All right, how's it going, everybody? We are here on Friday, February 5th, and we are going to talk about integration by parts today. We're going to talk section 7.1 here. And so just kind of get our context of where we're at right now. We started the semester with, all of chapter 5 happened in week 1. That was really our introduction to integration. So that was the basics of integration. Chapter 6, we looked at our basic applications of integration. We saw some volumes based on revolution. We saw work. We saw average value. Now that we're starting chapter 7, we're now going to be on to advanced integration techniques, right? So we're going to kind of change gears again and go back to saying there's more stuff we want to integrate. You saw at the end of that 6.5 video, there was an integral we wanted to look at, but we didn't have the technique yet. I was getting one day ahead of myself on that one, but I figured I kind of might as well. And so the point is, there's lots of integrals we still don't know how to handle. So we're going to come back now in chapter 7 to say we want to really buff out our integration knowledge here. There's still lots of rules that we don't know the partner of, derivative rules that we don't know the inverse partner of. We really haven't talked about trig functions at all this semester. There's a whole mess of trig stuff we're going to talk about next week. It's all trig next week. 7.2 and 7.3 are two different sections on what happens if you've got some crazy trig stuff in your integrals. You guys already saw that, and I think it was the 6.2 My Open Math homework with some cosine to the fifth and stuff like that. And those problems, Mom was telling you what you should do for the substitutions, but what we want to know is how do we know what we should pick for the substitutions without somebody telling us? The other situations that are going to come up in the next two sections is that there's going to be some integrals that don't involve trig functions whatsoever, and it's going to benefit us to mash some trig functions in there, to substitute in some trig functions to actually help make it easier, which sounds sort of unbelievable when I just say it. Other sections that we're going to see as we also want to discuss what happens when we have limits that involve infinity. What happens when we try to integrate over a function that maybe diverges off to infinity over somewhere in the bounds of integration? Or how do we handle bounds of integration that include infinity? How do I integrate from 0 to infinity some integral? What sense can we make of that? So in chapter 7 here, we're going to get our more advanced integration techniques. And then again in chapter 8, we're going to flip back over again and say, now that we can do a bunch more integration, let's see what types of applications we can do with these new skills. That will be chapter 8. And so the first 4 chapters of this class are learn some integration, do some stuff with integration, learn more stuff about integration, do more stuff with integration. Those are the first 4 chapters. That's 5, 6, 7, 8. Then we're going to skip over chapter 9 because that's differential equations. I believe is my chapter count right there. Anyway, the point is the back third of this class is all going to be chapter 11, and it's going to be a big change of gears here. So we're kind of setting ourselves up for what I consider to sort of be the middle third of the class. We sort of get like easy integrals and integral applications, then hard integrals, hard integral applications, and then sequences and series is really kind of part 3. So today in my mind is sort of, in a sense, the beginning of part 2 of this class, which is probably the longest third of the class right there, so it's not really a third. Right? So let's hit it here. Integration by parts. This is going to be a cool day. This is one of the cooler techniques that we're going to learn this semester. One of the most important techniques we're going to learn this semester. This is one of those things where it's like if I had to pick 5 total days of this class that anybody actually remembered when this class is over, absolutely this is one of the ones that's on the list. This one's super important here. Comes up all the time. So let's get it. In general, since integration is very nearly the perfect inverse of a derivative, what we want to do is come up with integration rules that are going to undo our derivative rules. The chain rule, probably the most important derivative rule, and we found its partner, u substitution. This is like one of the first things we covered in this class, right? This was week 1. We talked u sub, and what u sub is going to do is it's going to help us with these nested functions where we have functions of functions. The chain rule is going to apply to those composition functions right there, and we can undo the composition with a u sub. That was really important. The next rules that you learn when you're taking Calc 1 are the product rule and the quotient rule. I hope that what you guys remember about the quotient rule is that it sucks. In fact, we can always get away with just never using the quotient rule if we want, by instead of thinking of a function as like, f divided by g, we can instead think of things as f times g to the negative 1 power. So that allows us to replace needing the quotient rule with a product rule combined with a chain rule instead. And so that's the thing that I do a lot of times is say, nah, I hate the quotient rule, not using it. I'll just do a product rule and chain rule instead. Rewrite a division as a multiplication to a negative 1 power. So basically, the bottom line is nobody cares to go further in depth with the quotient rule. It just kind of sucks. The product rule, however, is the really important one. And so, in a sense, today we're going to help find, in a sense, a way to undo the product rule. Now, that being said, I don't think that it's appropriate for us to necessarily think of this rule as the product rule for integrals because this is going to handle a lot of cases other than, this isn't just going to be like the integral of f times g. We're going to be handling cases beyond that. We'll see several examples of that today. But it's also the case that when we do have things that look like the integral of f times g, a product of two functions, it is the case that this integration by parts will help there. But again, integration by parts does more than that. It's not just a product rule. So let's take a look. Um, so to me, this is sort of one of those, in a sense, unbelievable formulas. Kind of like when I very first saw the product rule and the quotient rule. Both times I was like, that seems kind of ridiculous. Like, why would that be the way that it's set up like that? And in those cases, because I'm a reasonable person, I said, I don't really believe that's true. And I tested them against things that I already knew. And I convinced myself that they must have been true. Um, the good news for us is that there's going to be some relatively easy ways that we can construct this integration by parts formula on our own, in a sense, deriving the formula ourselves. And that makes me feel a lot better about this. I don't know. Maybe this is just one of those things where it was taught to me this way and I just don't remember it as that goes. But this is something where I didn't feel like I'd seen before till I was teaching this topic. And then once I was teaching it, I was like, oh, of course, that's easy. Why didn't I know that before? So I think that there's a lot of value in you kind of remembering these derivations right here. So we're going to derive the formula that we're going to use all day today. We're going to come up with two different ways that we can derive this formula, two different ways that you can build this with just your own knowledge and come up with the integration by parts formula on your own. Then we'll go ahead and look at some applications of integration by parts. So we want to derive the formula. I should get rid of justifying. I'm not giving you the formula. We're deriving the formula. Deriving the formula for integration by parts. So we're going to do this two ways. One way we're going to do this is we're going to start with the product rule for derivatives, and we are going to just use the statement of the product rule for derivatives to determine the integration by parts formula, only using the product rule from derivatives. The second way that we're going to come at this formula is we're going to draw a picture and we're going to kind of compare some geometric regions in the picture. We're going to state some simple statements about areas of rectangles and it's going to lead us to the integration by parts formula. So two very different perspectives on arriving at the exact same conclusion here is what we're going to do. So let's go ahead and do the dang thing here. So my claim in number one is that from the product rule for derivatives, we can go ahead and build what is known as the integration by parts formula. And by the way, integration by parts, I will shorthand this as IBP all the time because I'm not going to write out a three-word phrase for a very commonly used technique. So IBP, the rest of the semester, that's integration by parts. And another thing is that it's pretty common to hear, I've heard lots and lots of professors just refer to this as parts or saying things like, oh, you just got to parts it. Using parts as like a verb, even with the S on the end, which sounds wrong, but then that's kind of how I know that that's the special version of integration by parts, or you just got to use parts on that one, integration by parts. So these are some kind of typical shorthands associated with this somewhat long name of a very important strategy here. So let's do it here. So product rule for derivatives. Let's state it. Product rule is the derivative of some f of x times g of x is, we're going to get the derivative of the first with the second left alone, plus we're going to leave the first one alone, and we're going to take the derivative of the second. All right, so f prime g plus g prime f right there. I feel like I usually verbalize that separate. Doesn't matter. Best part about the product rule for derivatives is it's all multiplication and addition, which means there's no way to get it wrong. You mix up any of your parts and it's all still good. Multiplication and addition are always commutative there, so it's really hard to get this formula wrong right here. So all I'm going to do is I'm just going to take an integral on both sides with respect to x. The integral of the derivative is just going to give us the interior component here, the f of x g of x, right? So that's all that's going to happen on the left-hand side here. On the right-hand side, when I take my integral, what I'm noticing here, that's what I'm right and wrong. Where's my, here we go. Let's try that again. F prime of x, g of x. And I'm going to rip this apart now Okay, I'll write out the whole thing right here. But the point is, since this is an integral of a sum, I'm going to rip this apart into two integrals here. I'm going to write this as f prime of x. And importantly, so I'm gonna change my order ever so slightly. I just said an arbitrary fact about the product rule, and it turns out I actually care about it right now. I'm just gonna write these where the derivative term is second on each of these integrals right here, just for a little organizational purposes. Doesn't really matter because it's all just multiplication, but it's going to help us see kind of the way that we're setting this up here. A typical thing that we do with this formula here is we use some different variables. Sorry, let me see how much room I got right here. I think a good way for us to think about integration by parts is it's a little bit more of an advanced substitution technique, basically. In u substitution, we created a single new variable of u. In our integration by parts, we're going to create two new variables, a u and a v. So it's sort of like a double substitution. And so I'm going to create those u and v variables now. I am going to refer to these as, and I'm going to just maybe, I think I'll just do this for this whole thing here, try and do all my substitutions today in blue for organizational purposes here. I am going to choose my u variable to be f of x. And as we typically do with u substitution then, I'm going to refer to this du as f prime of x dx, right? You should be thinking to yourself du dx equals f prime of x, and then I multiply dx up to the other side. The other substitution that I'll make is I'm just going to call v our function g of x, and therefore, very, very similarly, dv is going to be g prime of x dx. This block of four terms that we need to come up with, you're going to do every single time you do integration by parts. And this one, it's just a very generic renaming, but there's actually going to be functions of x in there that you're actually taking derivatives of. We'll see the action of this, but again, this stuff in blue is going to happen over and over and over again here today. All right. So based on those two substitutions that I just made, I can go ahead and rewrite kind of all the terms that I've got in this scenario right here. It looks like on the left-hand side, this is really just the same thing as u times v. And on the right-hand side for my integral here, I've got the integral of g of x I called v, f prime of x dx, f prime of x dx is what I'm calling du, plus the integral of, over here, f of x is u, and g prime of x dx, that's dv. And so all I'm going to do to rewrite this formula ever so slightly and be done is the whole purpose of this integration by parts formula is it's going to say, you've got an integral that you don't know how to handle. Let's rewrite it as a term plus another integral that maybe we actually can handle. It's going to be a slightly rewritten integral right there. So basically all I'm going to do is just solve for the second integral right here, this integral of u dv, and honestly it could be this one. It's just the typical convention is to have this be what we're solved for here. And in doing so, it looks like I need to subtract over this integral of v du to the other side. And so I'm going to get for my integration by parts statement is u dv equals uv minus integral v du. And this is going to be our integration by parts formula. And what this formula is going to do for us is it's going to say if you have an integral like something on the left-hand side over here, if you can identify what you believe belongs in the u parts and what you believe belongs in the dv parts, then from u we can determine du, from dv we can determine v, and that will allow us to fill out the right-hand side. And the hope is that uv is just a term that we don't have to integrate now, so it should be good to go. And the hope is that this integral of v du is going to be something that is simpler for us to handle than the integral of u dv. So the point here is we're sort of doing an integral swap, right? We're saying let's, in a sense, pick off some of the parts and hopefully end up with a simpler integral remaining than we started with before. It's a little bit hard to see like how this is going to work out in effect right now as we're just kind of deriving the formula. But the point is, this is our integration by parts formula, and it really just came from us stating the product rule for derivatives and taking an integral on both sides and rearranging some terms and renaming some terms. There was nothing really super special that just happened right here, right? We took the integral of a derivative rule and we renamed some parts and we shuffled some stuff around. We're going to see why this is actually practical and useful once we get an example. I think that this formula right here It's one of those things where it's like, well, I guess I believe that that's true, but who cares is what I think you should be saying right now. It doesn't seem why that's going to be a useful thing. It looks like we're just replacing an integral with an integral. The whole point of the strategy that's associated with is smartly choosing u and dv so that this second integral becomes easier than what the first was going to be. That's the point of this here. So what I want to do is I want to derive this formula a totally different route. I want to do geometry and set up some geometric integrals that are going to help me see this quantity here instead, right? So again, I think it matters to know where this comes from, which is why I'm deriving this twice. So I do think it's valuable to follow along with this so that you believe this. This is a kind of crazy looking formula right here. Why should this be true? I think that everybody likes proof by rectangle because everybody can get on board with that. So let's go ahead and do that here. So this is our geometric justification now. So what I'm going to do is I'm going to draw a really generic function here. I'm going to put it in the first quadrant just for convenience right here. It doesn't really matter what it is that we're looking at right here. So there's some curve that's out there in space right now. I'm going to call this curve some f of u equals v. Right? So that's saying I'm considering u to be my input variable and v to be my output variable. So I've got a u and a v axis. But something that we've learned, and like especially in our like cylindrical shells and our disks and our washers, is that there's plenty of times where it's meaningful for us to instead take our y equals f of x equation and turn it into an x equals like g of y equation, right? To resolve for the alternate variable and to get an equivalent relationship, but where we've solved for the opposite variable. So what I'm thinking to myself is it should be the case that there's a way to rewrite this function so that it's instead looking like v equals g of, or wait, no, I'm writing that backwards now. That's not what I'm trying to write. I'm trying to say instead of thinking of u as the input variable, we can think of v as the input variable. So I could instead think of this as g of v equals u, where I'm thinking of plugging in a y-axis value and getting out an x-axis value. So this is just saying like we solve for y or we solve for x, and I'm just naming them u and v so that we stick with our lettering conventions that we've got right there. So in this case, I am going to actually do this, by the way, using a definite integral. So I'm going to identify a region over which we're interested potentially in computing some values here. So maybe it's the case that we are interested in integrating this, this f of u function from u1 to u2. And what that would do is it would give us the area in this region right here, right? So I'm going to go ahead and I'm going to kind of mark this off here. This region right here, I want to name this thing so that we can talk about its relationship with some other regions. I'm going to sort of identify it right there. I'm going to call this region, I'm going to call it A2 just because the region above it's going to be A1, and then I've got A1 and A2 in order right there. The other region of interest for us is to say, well, you know, the other way that we could think about this is if you plug in U1 into the f function, you're going to get out v1. And if you plug in u2 into the f function, you're going to get out v2. So it seems like another thing that we could do is we could take in a sense, a sideways integral here, right? This integral of maybe thinking about the g of v function. If we integrated g of v, it's still describing this curve, but now area underneath the curve is no longer a vertical area underneath. It would then be a horizontal area over to the y-axis because we're integrating, this is a flipped thing, right? This would be like an x as a function of y thing, so this would be giving us the area towards that particular axis, the y-axis in that case right there. All right, so what I'm going to do here is I'm now going to do the exact same thing where I'm going to say, let's make sure that we understand that this is a region of interest right here. And I'll call this region here A1. So here's kind of what I want to see here with this guy. I'm gonna define each of these now. Now it looks to me like, what is A1? Well, A1, if I'm looking at this region A1, to find A1, this is a little bit weird. This isn't typically the way that we do integrals, but you can imagine just like we normally do like an integral of x squared gives the area underneath the x squared graph vertically. Well, that's y equals x squared. If instead we solve that equation the other way, okay, x squared is a bad example because it gives us that plus or minus if we try and solve it the other way right there. But instead, if we solve that equation for x instead of solving it for y and integrated with respect to dy, then that would be saying for each of the vertical heights, accumulate a sideways rectangle. That would be giving us the area under the curve, but really we mean between the curve and the particular axis with which we're integrating with respect to, right? In that case, the y-axis. So that's all I'm really trying to say. My roundabout way right there is to say this should be the integral from v1 to v2 of, and I know that what I need in here is a whole function of v, g of v, dv. And it looks like, based on how we've defined this, another way to write this would be v1 to v2 of u dv. We're seeing the terms like we were building up above. A u dv in there, so that's kind of like my u dv I've got right there. It's going to be one of the ways that we're going to think about this, right? Now, my area 2, very, very, very similarly, this is our little bit more traditional one here, u being our input variable. That seems like it's the integral of f of u from u1 to u2. Which we can rewrite as u1 to u2 of v du. And here's the important thing that we want to really recognize right here. I'm going to kind of get rid of the extra parts in my drawing right there. All right, if we identify these locations here as, right, our u1, our u2, our v1, and our v2, then all we've really done is, what we've done is, if we were to add these two guys together, and what we've done is we've created almost a whole rectangle. It's like a giant rectangle with a little rectangle missing, right? That's the area that we've in total covered with the two of these graphs together here. So what I want to do is I'm going to add together graphically a1 plus a2. And the way that I'm going to indicate this is like this. When I add together a1 plus a2, what I'm getting is sort of this L-shaped rectangle, right? It's getting the area under it plus the area to the left of it between these points. But notice it like discludes that little rectangle there in the corner. So this is going to be giving me this region right here. And the way that I can think about this is that this should be the entire big rectangle minus that little rectangle that's missing in the corner. Right? Does that make sense right there? I'm just chopping out the little corner right there. So it seems to me like it should be reasonable for me to add together these two integrals, a1 plus a2. That's going to be the integral from v1 to v2 of u dv, plus the integral from u1 to u2 of v du. That's a1 plus a2. And what this should be equal to is it should be equal to the entire area of that whole rectangle minus that little tiny area down there. Now, it looks like in this shape right here, it looks like the entire giant rectangle goes from 0 to u2 and then 0 to v2 right there. So the giant rectangle's area is u2, v2. It's just the two side lengths, right? Minus, what's that tiny rectangle's area that we missed out on, that little one in the corner? Well, it's got a length of u1 and a height of v1. So it's a u1 times v1 is its area. Now, have you ever seen something that looks like, your second parts minus your first parts? Well, yeah, that looks like when you've evaluated some integral from some second point to from some first point to some second point. You plugged in the twos minus plugging in the ones right there. This looks like our fundamental theorem of calculus, right? F of b minus f of a, right? Our antiderivative at b minus our antiderivative at a. So this really looks to me like a uv evaluated from our initial points to our final points, or our u1 v1 up to our u2 v2 right there. Right? And basically then, this is saying now we can go ahead and I'm just going to solve for one of the two integrals, and we're going to be sitting on our integration by parts formula. All I'm going to do is I'm going to solve for the integral of u dv by subtracting this guy over to the other side here, and that's going to give me the integral from v1 to v2 of u, that's a v right there, u dv equals, it looks like we're getting our uv evaluated from u1 v1 to u2 v2 minus the integral from u1 to u2 of v du. All I did was just subtract this integral over to the other side and write less words on my term right here. So this is good. This is again exactly our integration by parts formula, but this is just our integration by parts formula with bounds of integration. So this is saying to you, if you're evaluating a definite integral of u dv from bounds v1 to v2, then it seems like you're going to want to do the uv minus integral v du. But the only thing to kind of point out here is this uv term is evaluated over the bounds of integration that we've seen. And again, notice here that u1, u2, v1, v2, they're describing the same point in space, right? u1, v1 is a point in space. This is just like stating its x coordinate versus stating its y coordinate. But if you knew that the equation was like y equals x squared and I told you x equals 4, you automatically know that y equals 16 is an equivalent y value to be associated with that x value. So it's not like we're going to be given a u comma v. It's that we're going to be given just one of the terms, and depending on which variable we see in there, either the x variable or the y variable, we'll go ahead and plug in the appropriate constant that's associated with that. So all our only takeaway here is, the only real difference here is, yeah, this term that doesn't have an integration surrounding it, right, isn't part of an integral, it will get evaluated at our bounds of integration that are the exact same for both of these two expressions right here, right? This is just like in terms of x, this is just like in terms of y, or actually vice versa, but the point is, just a name, it's just a name of a variable right there. So what we've done is we've come up with this integration by parts formula once from the product rule for derivatives, once from this easy area argument saying we can find two curvy shaped integral regions where if you add them together, it really just gives you a region that's a whole rectangle minus a smaller rectangle. And that makes it something that we can easily state the sum of these two integrals is equal to a known geometric area. And then I just shuffled some terms around right there to state this in its more traditionally stated format right here. So we've got integration by parts as a formula. Integral of u dv equals uv minus integral v du. And we're going to use this a whole bunch today. We're going to use this more times than we're going to do examples today, because it gets hairy sometimes. So I want to tell you what we're going to do today and why we're going to do it and what you should be paying attention to. So let's just read everything that's on the page right now. And maybe, in fact, let's read this paragraph down here first. In general, you should acknowledge that this is one of the most important integration techniques that you're ever going to need to know. There's a ton of different scenarios in which this can be useful if you can see the setup. Sometimes seeing the setup is very easy. There are some formats where it's like everybody had better know that that's an integration by parts problem. Other situations, it is not at all obvious that integration by parts would even be helpful. And even if I told you that this is an integration by parts problem, it's still not necessarily going to be the case that you're going to see how to choose your u and dv correctly to make the thing work out, right? So that's going to be our struggle here, is this strategizing, this trial and error. So more so than for most sections so far this semester, you really need to for sure understand every single example that is in the book in this section, every single one of them without exception, right? So and we need to practice this a lot. There's a bunch of homework problems here. So I'm just going to tell you what we see in the homework, in the textbook right here. The textbook starts off with the textbook example number 1 is a very classic first example. There's like one of two problems that are like always everybody's first integration by parts problem. They did one of those two as their first example. We're going to do that example together. Example 2 is where we're going to see that we can actually derive the formula for the integral of the natural log of x. That's a formula that I told you you just needed to go look up on your first written homework. We're going to actually derive the formula for it using integration by parts as our example 2. The book does it. We're going to do it together. Example 3 and example 4 in the book are incredibly important. I'm not going to do them right now. You're going to read them. You're going to see why they did what they did. I'm going to ask you on the written homework to imitate some of the things that you see in the books, example 3 and example 4. But basically they're saying sometimes you've got to do integration by parts repeatedly to end up getting to a final result where you can actually manage to finish all the integration. That'll happen. Other times, like you're going to see in example 4, sometimes by doing integration by parts, it's going to take you in a circle to where you're going to come back around to where you started from. And you're going to say to yourself, well, that didn't do anything for me. I just got back to where I started and I just did a whole page of work to get there. And it turns out that going in a circle is actually a wildly useful thing for us to do with integration by parts, and you are going to see exactly why that's the case when you go read example 4 in the textbook. And I will, in the written homework this week, ask you a general form question about something that's very closely related to that example 4. So it matters that you read that guy and understand that guy right there. So 3 and 4 are honestly two of the most important, difficult usages of this. I'm going to leave those guys up to you. Actually, it's true that example 3, I got carried away, and our last example of the day is going to kind of contain that idea a little bit right there. But this cyclic idea that integration by parts will occasionally take you in circles in a way that seems useless until you notice what's happening, and then it seems very useful. You need to read that one and understand that one in the book. Super important. Finally, example 5. I know that most of you guys forgot a bunch of trig stuff, so we're going to do a little bit of trig stuff as our last example there. So, important. Lots and lots of different use cases here. This isn't something where you're going to look at a problem and say, hey, that's integration by parts. It's not necessarily going to be the case. And even if it is the case, making the right selections for your substitutions for u and v, not going to be obvious. We're going to see problems today where we're going to try over and over and over to see what the right setup is going to be before we finally land on the right one. So this takes practice. This takes intuition building. This definitely takes careful examination of the examples that are in the book to see what they did and what motivated what they did. Because again, I know that if I were to tell you guys what substitutions to do all semester, you could do all the integrals. The more important thing is that you know how to motivate these, that you can say to yourself, well, based on what I'm seeing, I think a smart guess would be blank and blank. And it matters that you're able to strategize like that. So strategy developing is really one of our important things here at this section. So let's start hitting some of these guys right here. And so I think I should probably restate my general formula here so that we can kind of remember what we're doing here. So our goal is to get things that look like integral of u dv to be rewritten as u times v minus the integral of v du. And our claim is that, our hope is that when we make this substitution, that this outcoming integral here is going to be more easy for us to integrate, or possible for us to integrate, as compared to the first, which we can't. And our first example right here, x times cosine of x dx, this is an immediate great example. First things first, obviously we don't have an antiderivative for this because it's a product of two functions. When did we ever get a product of two functions out from a derivative, with the exception of like trig stuff, right? Now there is trig in here, but it's a trig term and a not trig term, right? So that's like, what is it? The derivative of secant is secant tangent and stuff like that. I kind of actually see almost a little bit of that in here, but not quite, right? This is like a linear term times a trig term. The other thing I see here is that there's no chance that u sub is going to help us. What u sub helps us do is it helps us undo the chain rule. It helps us undo composition of functions. There's no composition here. We have a simple function x times a simple function cosine of x. There's no layering of functions together. It's just a product of two things. So in this case right here, this is going to be one where our integral here is going to look exactly like our format here. And that's not going to necessarily be the case in our future setups right here. So this is our sort of like slightly nicer one for us right here, right? So our goal always, and I'm going to scroll back up real quick, our goal always in integration by parts is to be able to determine what I'm going to just write in blue all day today here, the u, the du, the v, and the dv that are required to make this substitution happen. So choosing these four things right here, or rather I should say choosing u and dv, and then determining du and v from those choices to make this substitution, that's like the crux of our thing here. This is ultimately a big old substitution formula, so choosing the substitutions is really like the key step to make right here. All right, so let's go ahead and see if we can kind of make a selection here for ourselves. And I'm going to get over into blue for our sort of like side work here, right? We want this to look like u dv to be equal to uv minus integral v du. And here's the deal. We're always going to start right here. And we're going to get out this stuff right here. This is sort of like our output, right? So our intention is to try and interpret this as like a u and a dv. And in this guy right here, I'm just going to make some simple choices of u being x and cosine x dx being our dv term right here, right? So what I'm going to do is, and I'm going to scroll up again real quick. I personally, so I see a bunch of different ways that people write this stuff out. I always write my substitutions in a block that looks like this. I'm not saying that this is the more right way to write this. I'm saying this is the way that I've always written this. Consistency matters. You should pick something that's the most sensible organization for you and always do that same thing so that you don't confuse yourself. So I'm always going to write a U in my upper left and a DV in my lower right so that I end up with the U's and V's on top and the DU's and DV's on bottom. That's just it's just a thing I trained myself to do when I was in, this was probably my second semester of my senior year of high school, and I have always written my integration by parts like this. Choose an organizational format for yourself that's going to be good for you. So what it looks like the choices we're making here is U being X, and the other choice that I'm making is dv, right? U and dv are what we're identifying in our initial integral. Recognize that since dv includes the infinitesimal dv in it, it had better also include the infinitesimal associated with the integrand, right? The dx that's right there. So sometimes dv will include other terms like the cosine. Other times it won't. Sometimes we're going to pick dv to just be things like dx, a simpler form right there. And we'll see a bunch of examples. It's why it matters to do so many examples so you can see all the different things that we might want to do here, right? So when I choose my dv as cosine x dx, I now need to determine two new things. I need to say to myself, if u is equal to x, then what is du equal to? Well, this one's pretty easy. We've done a bunch of stuff like this with our u subs. That's just going to be dx, right? The other thing I need to do is I need to say to myself, well, if I have that dv is cosine x dx, what must v have been? And the reason that I always orient my work like this is because this allows me to think that moving down is a derivative and that moving up is an integral right here, right? U down to du is a derivative, but du up to u, that's an integral right there. So what I'm thinking to myself is I'm really sort of asking myself, what's the integral of cosine x dx? What did I take the derivative of to get cos x dx? And it seems like that should be sine x right there, right? So the blue parts are what we chose. The green parts are what we determined based on what we chose, but we needed these green parts because these green parts, notice that v du is exactly the integral we're going to be giving ourselves to then have to solve once we make our substitution right now. All right? So let's go ahead and do that. So it looks like I'm now saying x cos x, that's my u dv, equals u times v. That's my first term. So that's going to be x times sine x. Let me get my dx right there. Minus the integral of, and again, the whole point of all of this is we're trying to replace an integral we don't know how to handle with an integral we do know how to handle. I don't know an antiderivative for x cos x, but look what we get over here. V du is sine x dx. Easy. So we have replaced an integral we can't do with a term that we don't need to integrate, x sine x, and an integral that we can handle. That's great. This exactly achieved its purpose right here. Integration by parts is the only way I know how to do this integral, and it replaces an undoable integral with a term that we don't need to worry about with calculus, and an integral that's easy. So that's this really nice output right here. So we're getting x sine x. The integral of sine, what did we take the derivative of to get sine? That should be negative cosine. So it looks like we're going to get plus cos x. And certainly we should be getting a plus c on the end right here. And I'm claiming that that's our final answer right here. What I think a reasonable person should do would be to check this. Because we're going to get out some sort of unbelievable answers today. I mean, you couldn't have guessed that this is what our answer was going to look like. I couldn't have guessed that that's what our answer was going to look like. So I think that in a lot of these, you should be like, man, really? And you should check it. So x sine x plus cos x plus c. We know the derivative of c goes to 0, so I really don't even actually need to include that right here. The derivative of x sine x, we're going to get the derivative of x as 1. We're going to leave sine x alone. Plus, we're going to leave x alone. We're going to take the derivative of sine x. We're going to get cos x. The derivative of cosine is negative sine. C went to 0. Well, it looks like sine and negative sine cancel and leave us just with that right there, x cos x, right? So pretty cool. So our check is clearly good. We clearly got back to x cosine x like we started with by taking the derivative of our integral. So I'm confident that we got the answer right here by making these appropriate substitutions. Now, again, our goal today is not just to use a formula. You learn how to just use formulas when you take Algebra 1. Our goal today is to help think more strategy type stuff, right? So our first couple examples are going to be a little easier. I promise our last example is going to be harder, and it's going to depend on our ability to have a little bit of endurance, a little bit of grit to keep on going, and to think about, is that choice I made a smart choice or not? And should we make a different choice than we've currently made, right? So let's keep on looking at our next examples here. Example 2, which is also example 2 from the textbook. You were previously asked to know the integral of natural log of x, and I told you, go look it up in the book to do that problem, right? And it should have been in the back of the book. It's formula like, actually, I think it's formula 100 in your integral table back there, or it's something very close to integral 100. So let's see if we can actually see where that formula came from. Now, the thing I think is so weird about this does not immediately just slap me in the face saying, hey, Tony, do integration by parts. And the reason it doesn't do that is because what a simple function this is. There's not a product of functions, there's not a composition of functions, but I don't know an antiderivative for it, right? We're in a kind of weird place right here. So this doesn't just strike me directly as integration by parts immediately. But this is one of those things where it's like, well, I don't know, let's just try some stuff here, right? I also don't see any u sub potential right here because what would I do? Pick natural log of x to be u, then I need a du, which is a 1 over x, which I don't have any like 1 over x terms to help my du substitution happen. So I can't just do this with u sub right here. So the good news for us, though, is that strategy-wise, there are very few choices to make right here. Our difficult integration by parts problems are going to be the ones where there's lots of possible choices that we could make for u and for dv, and we might need to try several different setups before we get there. In this one, we have two components, natural log of x and dx. I don't really have a lot of choices available to me here, right? So I'm thinking to myself, I know this is going to be like some, let me get my appropriate color here. I know that I'm trying to match up with our formula here. Integral of u dv equals uv minus integral v du. And so all I'm seeing for my, like, I don't know, is there any other choice for us to pick other than this right here? I mean, this seems to be the only like sensible way to break this guy down right here. I only have two parts. I need to make two substitutions. Like those are the only realistic choices I think I can make here. So again, I'm going to set up my substitution table here. U, my choice is natural log of x. And again, I don't know that this is going to work out. I'm setting it up and trying. You really, really need to be open to the idea of trial and error on this stuff. You are going to make some wrong choices for U and DV, and that is okay. Try something else. Just try some stuff. Don't be afraid to just try some stuff. So my choices here for U and DV are going to be the only ones that are immediately obvious to me. Now, if this is going to work out, then it needs to be the case that du is going to be the derivative of natural log of x, which is 1 over x dx. I also need to say, well, what was x, or what would we have had for v here, right? So this guy we interpret down, this guy we integrate to get back up. Well, that one's also really easy. If v is x, then dv is dx right there. All right, so we've figured out what our four pieces might be. It's not clear to me still yet if this is the right way to go with this, but I'm just trying it right now. Okay, I've set up my attempted set of substitutions. Let's see if we can use this to rewrite this guy, and maybe this will, like, maybe we'll get an expression here, but we can't do the other integral or something like that, right? This is what I'm saying by trial and error. At this stage, it's still not clear to me if this was like a good choice or not, but let's try it. So what am I getting here? U times v, well, that should be x, or, natural log of x times x, or x ln x, minus the integral of v du. V is x. Oh, and how nice is that? Oh, man, that's nice. Ooh, x times 1 over x, well, I can do that. Ooh, Pretty cool. Wow, did that second integral turn out nice. It's the literal easiest integral on earth, the integral of 1 dx. There is not an easier integral than that. Um, Very cool. All right, so there we go. This is our formula for the integral of natural log here. And somewhat surprisingly, it comes from integration by parts. That's a surprise to me because there's just not that much stuff to work with right here. But it turned out that this technique gave us an incredibly simple integral as our replacement integral for natural log of x right there. And with all these ones today, probably I think we should check it right here. Our derivative of x ln x minus x plus c, again, plus c, I don't even know why I'm including it there. It obviously goes to 0. Our first terms here, derivative of 1, leave natural log of x alone, plus leave x alone, take the derivative of natural log of x, minus the derivative of x is 1, c goes to 0. Well, this right here is just natural log of x plus 1 minus 1, and those cancel, leaving us with natural log of x. So I feel really good about the answer that we just came up with right here. Cool. So deriving our formula for natural log of x, it looks like where that formula comes from is integration by parts. And it's just these kind of surprising things in calculus. I feel like it's not clear what derivatives and what integrals are going to be easy and which ones are going to be hard. I feel like natural log of x as an integral shouldn't be anything difficult, but it's like, well, when did you ever take a derivative and get out a natural log? And it's like, well, I guess I didn't. And so there we go. We now have an antiderivative for natural log. And this is one of those ones also, by the way, I just want to let you know, I have come across needing to compute an integral like this many, many times, and I never remember this formula right here. I just do the integration by parts every single time, right? So in a sense, we derived a formula for the antiderivative of natural log, but also like, I don't know. It's not like I remember this formula ever. I just redo this work every single time I need an integral of a natural log because this is a really easy parts to set up. And I know in my head, it's just one of those things where I've had to like look this up 6 times. And every time it's like, this formula comes from the integration by parts. And I'm like, oh yeah, duh, I can do that. And now I'm just like, I just have it burned into my brain. Integral of natural log, do parts. And I now know that that's a smart move to do right there. Cool. So we got our integral and we checked it and it worked right there. So again, be organized. We need to be able to set for ourselves up some of these, a table of substitutions right there, and make smart picks. So let's go ahead and keep cruising along right here. Whatever, Microsoft Word. Okay, example 3, which is example 5 from our textbook, the integral of inverse tangent here. Now, this is another one where you've never taken a derivative and just gotten out inverse tangent, but we do, this is like natural log, right? It's like, this isn't like some wild function. It's not a product of functions. It's not a composition of functions. So again, this is one that doesn't, like I said before, this doesn't just slap me in the face and say, Tony, do integration by parts. Like that doesn't happen right here. But I don't know what else I'd try, right? Like what other techniques do we have available to us? I don't have an antiderivative. I can't u sub it. There's nothing to even u sub here. The one really nice thing is it seems like there's very few choices for us to actually do the u sub in, right? Or to do the integration by parts right here. What options do we really have? So u dv equals uv minus integral v du. Well, I mean, what choices do I really have right here? That's kind of got to be the u parts. That's kind of got to be the dx parts right there. So let's see if we can do this. Well, if u is tan inverse of x and dv is dx, well, I've got one easy one here. But what the heck is this? So let's see a show of hands. Who remembers the derivative of inverse tangent? Oh, only I see 2 people remember the derivative of inverse tangent. All right, I don't need to be in person to be able to count that. It seems like all of you guys need a refresher on what the derivative of inverse tangent is and why we know exactly all of our derivatives of our inverse trig function. So let's go ahead and remind ourselves of what this should be. So our goal is to take the derivative of this tangent function, this inverse tangent function here, right? So here's the way that I like to think about this. We're looking at y equals tan inverse of x. We want dy dx. But what my issue is here is I don't, like the whole point is I don't know how to take dy dx. So here's what I'm going to do. I am going to apply tangent to both sides. And I am now going to do an implicit derivative right here because I do know my derivative of just tangent. It should be secant squared. But notice that y is an entire function of x, so we have to do implicit differentiation, right? There is actually a chain rule right here. So now I'm going to take my derivative of this guy right here. And this is going to give me secant squared of y times dy dx equals 1 because I took the derivative of x with respect to x and get 1, right? So it seems like what we should be getting for our answer here is that dy dx, what we're searching for, is 1 over secant squared of y, and 1 over secant squared should just be cosine squared of y, right? But the problem is, so now what's cosine squared of y? Let's rewrite original y. Or, sorry, let's see here. Oh yeah. Okay. Here's the note I really want to give on this guy right here. Let's draw the triangle. And what triangle? Well, let's draw this guy right here. Tangent of y equals x. Well, I know that tangent is a ratio of two side lengths of a triangle, so it's not helpful for me to see that the output is a number. I want to see it as a ratio, right? So I'm going to think of it as x over 1. The other thing I'm seeing here is that y appears to be being treated like an angle. We're taking the tangent of it. So this is an interior angle of a right triangle in my mind here, right? So here's my right triangle. We've got our angle of y. And I'm claiming that the tangent of y, opposite over adjacent, opposite is x, adjacent is 1. If we do a little bit of Pythagorean theorem right here, then we can see that this other leg that's up here should be the square of 1 plus the square of x is equal to the square of this side. So this is going to be x squared plus 1, the square root of that as our other leg right there. Our goal was to find, now we can see that cosine squared of y, which again is our answer, right? Our goal was to find dy dx. It's cosine squared of y. Now I can see that cosine squared of y is, well, cosine of y, cosine is adjacent over hypotenuse. So it's 1 over square root of x squared plus 1 squared. So it looks like our answer here is 1 over x squared plus 1, and that's our dy dx. So all that work right there was just so that we knew how to get our final piece for our parts, right? I didn't remember what my derivative of tangent inverse was, and now this is my derivation for tangent inverse that you guys learned in Calc 1, but I know this derivation's slightly hairy right here, and so that's why I felt like this is a good refresher right here. All of your inverse trig functions can follow some general form like this where instead of directly taking the derivative of an inverse trig function, we make an implicit equation, do implicit differentiation, and then draw a triangle to interpret the result of our answer because we're going to get a dy dx that involves y, and we wanted a dy dx that involves x. And so we had to get a triangle to help us out with our side lengths right there. Right? So it now seems like I can now make my claim. And what I should do is I'm gonna do this just to kind of keep a little color coordination right here. 1 over x squared plus 1. Right, that's what we just figured out right there in green. So we had to do a little bit of work right there, but we have rederived our formula for the derivative of tangent. And again, notice like some of the limitations here. Like the point here is that like whatever you pick for u, if you can't take its derivative, then you can't use that for u for integration by parts. Whatever you pick for dv, if you can't integrate it, then you can't use that for your dv for integration by parts. We still have some like a little bit of roadblocks to get over. In our first two example, finding du and finding v were easy, but that's not always going to be the case. Sometimes you're going to make choices of those where you're like, oh crap, I don't know what to do with that thing now. I can't integrate that dv to get a v. Then you can't pick that for dv. And so that's kind of one of our potential limitations here. So it looks like we've got integral of tan inverse of x dx is going to be u times v, which is x tan inverse of x, minus the integral of v du, which is x times 1 over x squared plus 1 dx. So I'll write this as x over x squared plus 1 dx. So, did we help ourselves? Did we do ourselves a favor? And the answer is technically yes. It looks like we still have some work to do, right? So this integral we straight up don't know how to do. This integral, I think that we do, but it's going to take us a smidge of effort, right? It looks like I have x squared stuff in a denominator and x stuff in a numerator, so it feels to me like it would be appropriate to now u sub this thing. Although I don't know, I don't really want to repeat any variables right here. So now we want to do let's do some u sub, but I don't want to repeat a variable. So I'm going to just do like a t substitution or something like that, right? Get a new color here. So what I think I want to do here is say that the integral of x over x squared plus 1 dx, I think I want to do something like t equals x squared plus 1 dt equals 2x dx. And I don't have a 2, so I'll shift that over to be on the dt side of things here, x dx. I do have an x times dx, so that'll be an appropriate thing to do here. So this should be, is going to become, what do we got here? Just x dx is going to be 1/2 dt, and that's a 1 over t, right? Because x squared plus 1 is t. And so that's going to give me 1/2 natural log of t, which I can rewrite as 1/2 natural log of x squared plus 1. All right, so I did my u substitution that I needed to do to complete my integration by parts. Start getting used to that. And now it looks like I can state my final answer for this thing. It now looks like I can say that my integral of tan inverse of x is equal to x tan inverse of x minus, and what exactly what we just got right here, right? We're subtracting off, it looks like 1/2 natural log of x squared plus 1, and we'll be responsible and keep our plus c on the end right there. Pretty sneaky roundabout stuff right here, right? So we had two kind of big bonus steps that were involved in this one. One, which is we actually have to remember Calc 1 because there's derivatives and integrals involved just in making your substitutions for integration by parts. And then our integration by parts led us to an integral that required us to do a u sub. But do me a favor, never reuse a variable that you've already used in that problem unless you've completely walked away from the substitutions that you're making here. It just makes things a little bit tougher. And I'm thinking right now, I'm going to break that rule slightly later, but that's because we're going to have so many substitutions we're about to make in a problem that it's going to be hard to avoid the repetition out there. But be smart for yourself. Use V's, W's, T's. I try and avoid S's because they look like 5s when I write them. But like, pick broader variable choices for yourself to kind of make these things happen right here. And we can come up with all the things that we need right here. So I think one of like the features of integration by parts that's kind of the most important is less so your mathematical ability and more so your persistence. If you give up easily, then you are going to have a really hard time with this. This took a lot of steps right here, and you need to keep on saying to yourself, either I need to abandon this trajectory that I'm taking right here. I don't think this part setup is going to work. Or you need to say to yourself, all right, I can do this next step. Okay, I can do this next step. Okay, I know how to do that integral now. And keep on rolling with this. This takes, none of these are just like one steppers. You're not just throwing something in and getting something out right here. A lot of these take a little bit of effort and more than one process combined in here. Expect that. Make sure that you are thinking about your mathematical endurance along the way here, and that it matters that you can keep on pushing through a problem even when you get to a part where you're like, oh shoot, I don't know that. Go look it up, rederive it, do careful variable substitutions, don't introduce any repeat variables so you confuse yourself. Obviously, it's convenient for me to get to use color and stuff like that to kind of guide my thoughts right here. It's not something I usually have when I'm on paper. Maybe you want to, I don't know, introduce some color somehow into what you're doing. I don't know. Be organized, be persistent with these. It really matters. So, our next one here is excellent. This is a great example of what I mean when I say you had better develop some persistence. And this will be our last example of the day, but this one's going to take us a hot minute to feel our way through this one right here. So this is important that we do the full duration of this guy right here. So here we are. Two things that are different about this than the previous. One, obviously this is a definite integral. We're going to do this guy from 1 to 2. That's not really going to introduce too much difficulty for us. That just means that we're going to evaluate the outputs from our integral from 1 to 2. And remember that that UV term that we get will also be evaluated from 1 to 2. We saw that when we did our geometric derivation of the formula. The other thing that's really important to see here is it looks like we have we have new parts that we haven't seen in our previous like 3 problems, right? Not only do we actually have a product of 2 functions in here, but it looks like we also have a composition of functions right there as well. So we've kind of got things that actually do make this look, I mean, this is a problem where when I see this guy, I do think to myself, oh, maybe I need to be parts in this thing. That thought does occur to me in this one because I see some indicators that honestly, we weren't really seeing those indicators in the previous problems. Those are just straight up integrals of a single function. It turned out that parts helped us get there. These are the ones that visually look to me like something that I can parts my way through. So we kind of know our process by now, right? We know that we want to think that we're looking at some sort of like u dv should be equal to uv minus integral v du. And so we're just going to make our like most natural first guesses here, right? So I'm thinking to myself that we should try to do like picking u to be x to the 5th. We'll need to come up with du. I'm thinking that we could pick a dv to be e to the x squared dx, and then we need to come up with a v. So I can take my derivative of x to the 5th, and I'm going to get 5x to the 4th dx. Over here, I need to come up with an integral of e to the x squared. Oh, shoot. Not possible. There is no antiderivative for e to the x squared. You need an extra x multiplication in there so that you could do a u sub to make that happen, maybe. Well, that's disheartening. So it looks like this isn't going to work out for us. I straight up don't know how to get a v. There's not a with this selection of u and dv, it is not possible for me to determine what v is going to be. So therefore, I can't use this as my choices for u and dv. I have no way to complete the problem, right? So it looks like we need to make a second set of choices, right? So here's what I saw my issue was. I don't know how to integrate e to the x squared, so I had better not include e to the x squared in my dv component. Everything that goes into dv needs to get integrated to turn it into v. However, I can take the derivative of e to the x squared, and it's got to go somewhere. So it looks like I need to put my e to the x squared stuff in the u component instead, right? So maybe we pick it so that e to the x squared is the thing that goes in with u, because I could take its derivative. This is going to give me, I always get back everything from the e term times the derivative of the inside function. That's a 2x dx right there, right? And now if I chose e to the x squared to be u, then everything left over has to be dv. That's got to be x to the fifth dx. This is something I can integrate to determine what v actually was. That should be a 1/6 x to the sixth, right? Okay, so we were actually able to come up with it in this case right here. And so if we were to do this guy then this is going to lead us to say it looks like we're getting integral from 1 to 2 of x to the fifth e to the x squared dx equals uv remember that this is evaluated from x equals 1 to x equals 2, minus integral of v du. V du is going to be, let's see, 1/6 and a 2 makes a 1/3. And now we've got, it looks like a total of x to the seventh e to the x squared. Does this look like this is a good choice for us to be making? It kind of seems like we're going in the wrong direction here, right? All this did was replace an integral that we already don't know how to do with one that in a sense is even worse. We've just increased the power on x by 2. Right? So, in a technical sense, we were able to come up with the u and the dv that are like at least technically doable for us. We were at least able to rewrite an expression. I mean, this equality is at least true. It's not helpful to me though because it didn't increase my ability to actually identify what all the features of this thing are actually going to be, right? We just replaced x to the fifth e to the x squared with x to the seventh e to the x squared. That's equally as impossible and in a sense a little bit worse because that power on x is getting even larger instead of like getting smaller. Um, right? If that was x to the 1, then we'd like be in good shape, right? So it seems like this is going to be not a very good choice either. That's a bad choice right there. So we have so far tried to do integration by parts twice, and neither time has it worked out. Don't give up. We still want to keep on trying some things. And so I want to say to myself now I mean, just because I'm not going to give up doesn't mean I'm not frustrated. I'm frustrated by now, right? So now I'm like annoyed. I'm like, well, what the hell am I supposed to do? Well, I want to think to myself, like, what's the most annoying part of this problem? What's the thing that's the most obnoxious thing here? What's the thing that's really preventing us from doing the things that we want to do? Right? And notice that these failed for different reasons. The first one failed because we weren't even able to come up with v from dv, so we couldn't even identify all four needed components. In the second one, we were able to come up with all four needed components, but they produced for us an integral that was equally as undoable as the original. So it didn't like increase our positioning at all, right? It didn't help our stance. So both of our first attempts failed. And they failed for different reasons. But what I kind of want to ask is, so like again, this isn't just like the throw your hands up in the air and be like, oh, this is stupid. Like we still will like think, right? Like what's the thing that's jamming us up here? What's the hardest, crappiest part about this problem here? If you were allowed to change one component of the integral that we have to deal with right now, what's the one component of this integral that's the worst for us right now? And I am hopeful that you are in agreement with me that I'm not afraid of an x to the fifth inside of an integral. This e to the x squared sucks. I can't integrate it. If e to the x squared shows up in my dv, I can't do it. If e to the x squared shows up in this integrand, I can't do it unless the only remaining x component in there is x to the first. And I don't really see how we're just going to trim ourselves down to x to the first. So my answer to this, what's the most annoying, which in my writing, so that when everybody actually reads this later, they don't see my obnoxious word choice that I'm verbalizing right here. I say annoying, but I'm writing this as inconvenient, right? I think it's the e to the x squared. I think that this problem wouldn't be so obnoxious if I just had an e to the x. And so I'm going to get out my beaten stick, my calculus beaten stick, and I'm going to make it that way. All right? So here's what I'm thinking. My roadblock in both cases was that e to the x squared isn't something I can handle. E to the x is like one of our easiest integrals, right? It's the thing that doesn't change when you apply either a derivative or an integral to it. You just get back e to the x again, right? So my question to you is, how can I forcibly transition x to the fifth e to the x squared into something that just has an e to the x? Well, I think that I want to maybe do a little substitution on x squared right there, right? What? Come back. What I'm going to do first here is I'm going to say, let's go ahead and sub in. And I know I'm going to, well, okay, I know that. You don't know that. I'm going to end up doing substitution here. And just like I chose before, I'm just going to do a t substitution instead of a u substitution. If I choose t to be x squared, then that's going to give me that dt should be 2x dx, all right? Now, I know I don't have any 2's in there, so I think I'm going to do my little usual 1/2 dt equals x dx. And I'm seeing that this is going to be mildly reasonable because I do have a single x that can partner up with the dx right there. Right? So this is me just saying x to the fifth is really x to the fourth times x. I just ripped off one so it can be part of the grouping I want it to be part of. And now it seems to me like I have the integral of x to the fourth e to the t dt, and I'll stick my 1/2 out front that I know that I got right there. And so now I've got like a mixed integral, right? I still want this x to the fourth to be transitioned. Well, actually, that's going to work out just fine. It seems like x to the fourth should just be t squared. So it looks like, in this case right here, I think I just did myself a pretty huge favor. I just did a u substitution that allowed me to reduce my e to the x squared down to being just an e to the t. E to the t is good for me because I can do all my derivatives and integrals dealing with it. Now, I still don't know that this is actually going to be good for me, but I feel like this is probably a step in the right direction. This looks much more like an integral that I actually want to handle than the original did. And so now I'm asking myself, can I do like a u substitution? Well, u subs, again, like, could I do like another u sub? And I don't really think so because if I chose like t squared to be my u, then I would get like a 2t dt. But that t that's involved is a power, whereas dt is not. I don't have a t times dt in this expression, so I can't like u sub my way all the way to success right here. But since I do have a product of two things in my integrand, that's at least one of my light tips that says to me, maybe I want to be doing some integration by parts now. So now let's think with our simpler integral. Now let's go ahead and see if we can set up some part stuff. Well, I think a pretty natural choice for us right here. My first guess, and again, I don't know what I'm doing. I'm guessing. I want to really just emphasize that every single step of the way here, I'm like, I don't know, I could try this. It's literally what's happening in my brain every single step of the way right here. You have to get more comfortable with making a guess and putting it on paper and following it out as far as you need to follow it before you determine either, yes, this is the way, or no, this is not the way. You have to put guesses on paper. I'm guessing some stuff. It's okay to guess. It's so hard to see these things. You're not just going to be like, I know this is the right choice ever with this. Get good at guessing. And not even get good, get comfortable with it. Be okay with being wrong. There's nothing wrong with that. So my easiest guess to make right here, I don't know what the right choice is, but the first guess that I want to make is this. And I'm going to tell you why I think this is a better guess than some other options of guesses. So here's what I'm thinking to myself. Here's the reason why I think this is a good guess, and let me compare it to my other option of guess. My other real option here, other than this one that I just wrote down, would be to say that my u would be e to the t. The reason why I don't think that would be a great choice is because then t squared would be involved with the dv, and I would integrate it to get t cubed. That would be increasing the power that I'm going to end up having to deal with. However, if I always choose my polynomial terms to be the u choice, then I'm always taking the derivative of u. I'm always reducing them in power by 1, and that is sort of eliminating terms from the integrand, right? So this is definitely a general strategy thing right here is anytime you have a product of two functions in your integrand and you're doing parts, if one of the terms is a polynomial term like t squared, almost always you want that to be your u selection, because when you then compute du for your outcoming integral, it will have a one smaller power on that term right there. That's reducing the amount of stuff that's in your integrand. That's usually good. If instead t squared was part of dv, we would integrate and increase the power by 1, usually making the problem worse, like right there, right? This was we increased the power by 2. It's either the same or worse now because we've got even more stuff in the integrand. It would be nicer if we were decreasing that power. We decrease powers by making their selection to u parts. Now notice our v choice, or not our v choice, our v result is easy here. Our integral of e to the t dt is e to the t. Got that one. So let's now see if this is our better choice right here. Or not when I say better choice, a doable choice. Did this help us at all? Right. So I'm now going to get, oh, by the way, I have abandoned my bounds of integration. I'm going to come back to recollect those at the very end. All right. So I'm just going to keep on ignoring the fact that there's the bounds from 1 to 2, and at the very, very end of this problem, we'll kind of refigure out what we should have done with those. Let's deal with the integration right now instead of the bounds. So what do we got? Well, 1/2 is going to be cruising along for a ride on the whole outside, right? U dv is going to be rewritten as uv minus integral of v du. Integral of v du is going to be, so I'm looking at my parts, by the way, before I just throw them in there blindly. I want to do things like get my constants pulled out front, so like that 2 is going to go out front. And I'm looking at my terms. It looks like I have a t e to the t dt. So, was this a good choice for us? Well, it's good and bad. The bad thing is I still don't know how to do this integration right here. I don't have an integral for t e to the t. The good news is that I'm recognizing that in the previous step, I took t squared e to the t, and by doing integration by parts once, I reduced it down to a single power of t e to the t. So what my intuition is telling me now is I could parts this thing again, and it should drop the power on t again. And if the power on t drops one more time, then it's just not even there. And I should just be left with an integral of e to the t, which I can just straight up do and be done with this problem, right? So it looks like in this case here, every integration by parts is leaving the e to the t alone in the integral, but is dropping the power on t by 1. And so since it's currently a t squared, it seems that 2 layers of integration by parts would completely get rid of that t. So let's now just make essentially the exact same substitution choices for another layer of integration by parts. And I think it's going to get us there. So I'm going to pick u to be t, which gives me du as dt. That's like the key to the whole thing right there, right? We're taking a component that was in the integrand, and it's just giving us the differential term now. That's good. dv is going to be e to the t dt again, because that just means leave the e to the t alone. It just survives. It continues to be there. And it seems now like we're going to land here at, now we can go ahead and get maybe our last statement right here. So 1/2 times t squared e to the t minus 2. Now I'm opening up a whole new integration by parts, right? This is an integral, and now I'm going to get my uv minus integral v to u again. Now I've got uv t e to the t minus the integral of v du. V du, oh yeah, there it is. That says to me, we're done. I can do all of the integrals that are on the page. We're done, right? Now I just need to do, now that I know, sorry, I was going to draw my plus C. I got all excited. That's on the next line, but we're basically there, right? Let's go ahead and expand some stuff. Minus, oh, in fact, there is no plus C because we're going to do a definite integral. Notice right here, by the way, I distributed this 1/2 onto the first term and then onto the collective second term, meaning I took 1/2 of 2 and that just allowed the negative to come along for the ride. This 1/2 did multiply this entire second group right there by multiplying the 2 coefficient that was sitting out front. So I feel like I'm getting 1/2 t squared e to the t minus t e to the t minus e to the t. And oh man, one of the things, oh, that's a plus right there. Distribute that negative. One of the things that's so cool about this is I feel like I can literally see the integration by parts cascading down. We had this stuff and it didn't work out, but it popped out as a UV term when we got the TE to the T on the inside. Then the TE to the T popped out as the U part in our second one, and it left us with just the E to the T on the inside, and then we just integrated the E to the T. I'm literally watching the parts happen in my solution here as this power on T decreased each time that we parsed it until we just got down to something that we could handle. Now what I know is I want to evaluate this guy from x equals 1 to x equals 2. And so what I'm thinking to myself here is I'm going to scroll like a million pages back up until I find how we relate those things right here. Oh, it wasn't that bad. T equals x squared. I think that that means that to me, I don't want to mash my x's back in. I think I want to convert my bounds into being t bounds. So I think I'm just going to evaluate from t equals 1 to t equals 4. And here we are. And it looks like this is 8 e to the fourth minus 4 e to the fourth is 4 of them, plus 1 of them is 5 e to the fourth, minus I have a half of an e. And those two cancel out, so I just think I have minus half of an e. Boom. So we should summarize what the heck just happened in this problem here. This is a bear of a problem, but this is a super good one right here. I love this problem right here. So notice that we tried many things that failed to start, right? I think that those are the super reasonable guesses that we're looking at in blue for some integration by parts setups, but they just didn't work out for us, and they didn't work for two different reasons. And I hope that you would easily recognize that they don't work as well by seeing things like we don't have an integral for dv, so that choice didn't work. We can do this one, but I am certainly hopeful that when you see that your integral just got worse right there, that means sort of like maybe this isn't the direction that we should be going. We should abandon that direction, right? So we did 2 failed attempts at integration by parts to get started. We got all frustrated. I got pissed off and I said, damn it, I can't do this with e to the x squared in there. And so I said, all right, e to the x squared, we're getting you out. And I forced myself to no longer have that e to the x squared in there. I did whatever I had to do to get rid of it, and it turned out in this problem, the polynomial parts played nicely enough with me that that worked out, right? So I said to myself, I can't do this with e to the x squared. So I forced the x squared part to be gone. Allow your frustration to guide you. I often do hate-based mathematics, hate-motivated mathematics. I get angry at this stuff, and I use that anger as motivation rather than just walking away right there. I was angered by the e to the x squared, and so I did something about it. I got rid of the x squared part by just making a little substitution, right? So by doing a u sub to start, it allowed us to finally be in a situation where the integration by parts made sense. Then we learned what I think should be a very important strategic lesson for you. That is, anytime you have a product of two components in your integrand and one of them is a polynomial product, it's good to use integration by parts, and it's good to pick the polynomial part to be u, because then when you compute du, you will reduce the power by 1, and you're sort of chipping away at that thing, right? You're making it easier and easier and easier on what's inside the integrand. It turned out in this case that we had to do multiple layers of integration by parts to make this happen, because each layer of integration by parts reduced the power by 1. And we started with a power of 2, and we kind of needed to get rid of the whole dang thing to finally land at a doable integral of just integral of e to the t right there. That's just what we had to do. So this took 2 failed integration by parts, followed by a successful u sub, followed by 2 successful integration by parts for us to finally get to the end right here. This was 5 different substitution setups, 3 of which were successful for me to actually do this problem right here. That's not that unusual in an integration by parts problem. So this is what I meant when I said right before I started this problem is you need to develop some persistence and some endurance associated with your integration techniques here. Keep going. You have to just keep on going. These things will eventually be chipped down by integration by parts into something that you can handle. There are plenty of reasonable integrals that you will encounter in your life that will require several applications of integration by parts. I'm also going to point out, so this right here, let me scroll way back up. In these examples, the 2 that I said that I wasn't going to do, Example 3 says sometimes you need to do integration by parts more than once. I think that the book does something where it's like an x squared something something, kind of just like what we had right there. So example 3 in the book sort of looks like that one that we just did. Ours was a little bit harder though. And again, there's still some things that are going to happen that are like endurance related, where you can't just give up, where you need to say to yourself, no, there's still some way that I can modify these components to make my way to the answer. Example 4 that you all just absolutely have to read in the textbook and read carefully and fully understand. Sometimes when you do multiple layers of integration by parts, it will bring you right back to your original integral that you started with. And that's going to make you throw up your hands in frustration, but then you're going to stop and you're going to think really carefully, and you're going to read that example 4 in the book really carefully, and you're going to realize that re-arriving after multiple layers of integration by parts back at your original integral is actually an excellent way to arrive at your answer. And you're going to see that exactly in example 4. You're going to see that in the written homework for this week, because I'm going to specifically ask you to do one that's going to be just like examples 3 and examples 4 from the textbook. More work's involved with these, right? Like all these took me like a whole dang page. This one took me like 2 whole pages right here to do. And I would just like to say to you in the nicest way possible, get over it. These are effort-based integrals, which I like because I know that I am capable of just doing hard work. It's a way that I have always managed to set myself apart from my classmates, is that I'm lazy a lot, but I work hard when it matters. And this right now is that it matters case right here. So these examples that I did today, I really, really like all of these examples. They all showed us kind of something different about this, right? And so what you should be doing in all of this is feel very comfortable with just making a guess. Flop out some substitutions that you think are it. Don't worry too hard about strategizing in the early examples that you do. In your first My Open Math questions, you should just be trying stuff. But what our obvious goal is to, in the future, not waste a bunch of effort on bad guesses. So kind of in every one of these problems you do, go back and reflect on it after the fact and say, did I make that guess correctly because it was a guess? Or did I know that that was going to be the right choice for U and DV? If it was just a guess, can I convince myself that I should have known it? If that guess didn't work out, how should I have known that it wasn't going to work out so that in the future I don't have to waste my time making that wrong guess again? There's a huge amount of strategy that now is involved in doing these problems right here. And so when you're doing all of your open math practice problems and the small number of kind of hard questions I'm going to ask you to do for the written homework, just be thinking strategy. In on the one hand, integration by parts is technically just a formula, but man, I could give that formula to a student that knows how to do integration, and they're really still never going to actually figure out how the components actually work. Has my screen been small this whole time? Dang it, that's kind of stuff pissing me off. Integration by parts, heavily strategy based. There's tons of different combinations of stuff you can see in an integrand where integration by parts works. And what you want to feel out is, what if there's a natural log? What if there's a polynomial part? What if there's a trig part? What if there's an exponential part? What if there's a composition of functions in there? Maybe I want to do a u substitution first before I do my integration by parts. All of these different scenarios out there are going to hopefully suggest to you a different choice of your u and dv that are going to be the ones that are going to work out for you. It's my hope that you guys don't waste too much time on making bad guesses, but man, you really got to put guesses out on paper. Try stuff. You have to not be afraid to just try something here, see if it leads you in the direction that you want to go. Learn from your mistakes and learn from your successes. Always say to yourself, why did my choice work? Why would other choices not have worked? So that you're developing that intuition about the right and wrong choices for the substitutions to make, right? Really, really cool technique here. Leads us to some really, really cool problems that involve lots of steps that you could never anticipate before you're in the middle of doing the problem, which means you just have to do it, right? So, cool. I really enjoyed today. I am very much looking forward to seeing your slightly complicated problems that are going to be in the written homework here that I'll assign for the week. And that's our integration by parts. This thing comes up everywhere. As I said at the very beginning of class, if there were 5 whole days, just 5 days of this entire class that you actually remember, this is absolutely one of them. And in fact, I'd probably put this in the top 3, not even just the top 5 right there. This will come up in so many integrals that you will compute in the future. This is a very, very important technique that you have mastered, not just dealt with once. This isn't like I need to go look up my integration by parts formula again. You should have this burned into your brain by the end of this section, and you should have an intuition about strategy for selections of your U and DV associated with this guy here. So this wraps up our week 4 stuff. What we're going to see in week 5 is a whole bunch of trig. We're going to see problems that have trig in them that you're going to have to deal with, and you're going to see problems that don't have any trig in them, and we're going to jam trig into it to make it all work out. And in fact, the reverse version of what I'm talking about is right here. We're going to see that when we get integrals that look like this stuff, how do we know that they are actually better represented as trigonometric ideas, stuff like that? We're going to see all that stuff next week. So next week is basically like trig week of this class right here. And so for all of you that don't own your trigonometry textbook anymore, I will be posting a PDF in chat of that back table, the back sheet that has all of your trig identities. You are really going to want those for week 5 of this class coming up next week here. So just kind of keep that in mind, that trig week is coming next week in week 5 out there, and we'll see all that stuff then. So that wraps up our week 4 items this week of our kind of easier section on average value, and our, I don't want to call it hard, but our meaty section. I mean, this is just a big old hunk of calculus steak right here, right? Sorry to the vegetarians out there. There's just a lot of content in this 7.1, so get on into it here, and I will see you guys in office hours and next week for all of our trig stuff out there. Have a good one, everybody.